Hello everyone, myself Kiran Chudasama and here I am presenting my project Optimizing Power System Stability, Load Frequency Control with the MATLAB Simulink. In this project, supply and demand balancing in the face of dynamic load changes is emphasized as MATLAB is used to integrate AGC with the frequency and voltage management. So here is the outline of my project. First one is the introduction, then methodology. In the methodology, I will explain about LFC and AGC mathematical model development. Then the result discussion of the both model and the last discussion. Now I start with the introduction. Voltage and frequency stability are important tasks for reliable power system operation. AGC means automatic generation control. Adjusts generator output in response to load changes and system parameters. Here, main goals of the AGCs are to manage interchange power flows between control regions and maintain system frequency. The components of AGC are voltage regulation and frequency control. Main importance of the advanced approach is to address challenges from increasing power demand and renewable energy integration. In methodology, first I discuss about LFC model development. LFC means load frequency control. Here we can see the flowchart of this model. This development is based on MATLAB Simulink and I generated MATLAB model according to the mathematical development by using the transfer function blocks. And this block utilize for various components like controller, valve controller, turbine, generator, sensors. Similar feedback block is used for feedback response and we can see our reference signal should be constant. So constant block is utilized for the reference signal. Here the output of the LFC in terms of frequency. We can see the first graph of the step response of the frequency deviation. The peak time is 1.223, rise time is 0.418 and settling time is 6.8. Also, the percent overshoot is 54.80. We can also show that in amplitude when the rise is coming over there. The signal is highly overshoot over there and the response is very stable within 6.8 seconds, which is very satisfying result with this model. After the performing of the LFC on the MATLAB model, we observe in the second graph that the percent overshoot is very less and the model is little bit undershoot during the first half of the signal. But after that, signal is steady stable within 6 to 8 seconds, which is very satisfying result for the generating system. Based on this, we can control our system with very moderate way. So small type of generating units are using this type of operation for the system frequency control. In this slide, I discuss about AGC mathematical model development. Here is the flowchart of the AGC model. AGC is the modern approach of the advanced power system where we can develop or implement our system or connect our system on the grid. So our each and every generated unit should have automatic generated unit. By any malfunction during the falls or any ups and downs in the load coming over there, our system should be very stable. Now I am talking about my development of AGC model on MATLAB Simulink. I perform mathematical operation in my project report. While we are working with the MATLAB Simulink, we have to our system with the same type of differential equation and we can implement them on the transfer function blocks. So different type of blocks are over there and develop this model is very complex. but the outcome will be very useful while we can govern frequency and voltage. So we can get satisfied output in the terms of power. Now we are observing the AGC output in terms of frequency. First graph shows noticeable undershoot below 54 Hz and overshoot above 61 Hz, stabilizing at 60 Hz after approximately 10 seconds. Second graph demonstrates smoother response with a quicker stabilization around 60 Hz within about 5 seconds, indicating enhanced frequency stability and system efficiency. Now moving further, AGC outcome in terms of voltage behavior. Here we can see two graphs of terminal voltage at 0 reference input and terminal voltage at 1.5 reference input. We can see the system voltage output is highly stable. First graph shows an early spike to 1.6 per unit followed by the oscillation, stabilizing around 1 per unit within 10 seconds. In second graph, effective voltage control with initial peaks about 16,000 volt, stabilizing around 12,000 volt, quicker than the first graph. And last, here AGC outcomes in terms of power. We can see the graph of delta power at 0 reference input and delta power at 1.5 reference input. First graph initially exhibits a power increase above 500 megawatt, oscillating around 3 megawatt before stabilizing after 10 seconds. Second graph similarly initial increase but stabilize after around 5 seconds, suggesting more effective control system with reduced overshoot. So I already discussed about the result of different graphs such as frequency deviation, power deviations and terminal voltage behavior of AGC model in the previous slides. We can observe that AGC output is quite better than LFC for larger unit in power generation. So in the discussion, the comparative study highlights the second AGC system operates more effectively overall compared to LFC. It demonstrates less overshoot and quicker stabilization in frequency and power variation, along with the improved management of terminal voltage. These enhancements contribute significantly to maintain stability and efficiency in the electrical grid. AGC plays an important role in maintaining stability amidst evolving power system challenges. Further advancement in AGC will enhance grid resilience and efficiency. Although LFC is still in operation at some power station, the AGC is modern concept of advanced power system. Thank you everyone.